Have you ever wondered why the plastic handle on a hot frying pan doesn't just melt? Or what exactly a bowling ball is made of? Well, today we are diving deep into a really special class of materials that, once they're formed, they are set for life. We're talking thermoset plastics.
So let's just jump right in with a question for you. Think about a bowling ball, the handle on that skillet we just mentioned, and maybe even your kitchen countertop. On the surface, they seem completely different, right? But they all share one fundamental secret. Any ideas what it is?
And the answer is, they're all made from a type of plastic that you simply cannot remelt. Unlike most plastics you run into every day, once these are made, that's it. The change is totally permanent.
I love this analogy because it makes the idea super clear. See, most plastics you know, like the stuff in water bottles or Lego bricks, those are called thermoplastics. They're kind of like butter. You can melt them down, let them cool and harden, and then melt them all over again. But thermosets, they're like an egg. Once you cook it, you can't uncook it, right? That chemical change is a one-way street. It's permanent.
So, let's get into the science of what's actually happening here. A thermoset is a polymer that gets cured, usually with heat or a chemical catalyst. And during this curing process, this incredible thing called cross-linking happens. Just imagine all these long spaghetti-like chains of molecules. The cross-linking builds these tiny, super strong bridges between all of them, locking everything into a rigid three-dimensional web. That cross-linking is the cooking from our egg analogy, and it's what makes the final material so hard, so strong, and so heat-resistant.
All right, so here's the game plan for this explainer. We've just covered the basics of the unmeltable plastic. Next up, we're going to look at how they're actually made, from scratch. Then we'll meet a few of the all-stars of the thermoset world. And finally, we'll dive into the two key ways we shape them, compression and transfer molding, before putting them side by side for a little comparison.
Okay, first things first, the recipe. How do you actually create a material that goes through such a permanent, irreversible change? Well, it all starts with some surprisingly simple chemical ingredients.
These starting ingredients are called monomers, and they're the basic building blocks. We're talking about things like phenol and formaldehyde, which, when you mix them, make that famous old-school plastic Bakelite. Or you might take melamine, which ends up in super durable dinnerware. Bisphenol-A and Epichlorhydrin, those are the key ingredients for most of the epoxy resins out there. So you can think of these as the specific flour, sugar, and eggs for our different chemical recipes.
Now, the process of mixing these monomers together is called polymerization. When you combine them, a chemical reaction kicks off, and they start linking up end to end, forming these super long chains we call polymers. This process turns the simple, runny liquids into a thick, gooey resin. It's basically like a chemical batter that's now ready to be poured into a mold and baked.
So now that we have our batter, let's see what kind of amazing materials we can make with it. It's time to meet the Thermoset All-Stars, a few of the heavy hitters you'll almost certainly recognize.
And our first all-star is phenol-formaldehyde, but you probably know it by its much more famous trade name, Bakelite. This stuff is a legend. It was one of the very first fully synthetic plastics ever created, and it absolutely changed the modern world.
And this is exactly why it was such a big deal. Bakelite is incredibly hard and rigid. It's a fantastic electrical insulator, and it can really take the heat. These properties made it the perfect material for things like pot handles that need to stay cool to the touch, or the casings for early electronics like radios and telephones that had to be tough, safe, and durable. Okay, next up is a material that I guarantee you've used yourself at some point: epoxy resins. Seriously, if you've ever used one of those super strong two-part glues, you have worked with a thermoset. Epoxy is just legendary for its incredible stickiness, its adhesive strength, and its resistance to chemicals and physical damage. And that's why it's used for so much more than just glue. You'll find it in heavy-duty protective coatings for factory floors, and it's also used to completely encase sensitive electronics, protecting them from moisture, vibration, and shock.
So we've got our thermoset batter, but how do we actually shape it and cook it into a final solid product? Well, the first major method we're going to look at is called compression molding. And honestly, the name gives you a really good clue about how it works. The whole process is actually pretty straightforward. First, you take a very precise amount of that polymer resin, they call it the charge, and you place it into the bottom half of a heated mold. Then, the top half of the mold comes crashing down, applying a ton of pressure and heat. That pressure forces the material into every nook and cranny of the mold, while the heat is what triggers that permanent cross-linking, the curing process. After just a little bit of time, the mold pops open, and out comes your finished, solid part. You can almost think of it like a heavy-duty industrial waffle iron. So why would you choose this method? Well, the big advantages are that it's a pretty simple process, and the molds themselves are less expensive to make. It's especially good for making big, relatively simple parts, like, say, those countertops we talked about. Now, the trade-off is that it can be a bit slower, and it's really not the best choice if you're trying to make something with a lot of tiny, intricate details.
So for those more complicated parts, we need a different game plan. And that brings us to our second technique, transfer molding. Now, this is a little more complex, but it gives you some really powerful advantages for detailed designs.
Okay, pay attention, because here is the key difference. Instead of putting the material right into the open mold, you put it in a separate chamber up top called a pot. You heat the material in that pot until it's nice and molten. Then a plunger comes down and pushes, or transfers, that liquid material through little channels and into a mold that is already completely closed. This is huge because it lets the liquid flow into very small, complex shapes before it starts to cure.
All right, so we've looked at both methods now. The big question is, when do you use one versus the other? Let's put them head to head so we can make it really, really clear.
This table really breaks it all down. For part complexity, it's a clear win for transfer molding if you're making something intricate, while compression molding is your go-to for simpler stuff. But that complexity comes at a price. Look at the tooling cost. It's higher for transfer molding. And here's another interesting trade-off. Transfer molding is often faster for each part you make, but it also creates more waste material because all that leftover resin in the pot and channels gets cured too, and you can't reuse it.
So, what's the bottom line here? It's that there's no single best method. The choice between compression and transfer molding is always an engineering decision. It's a balancing act, a trade-off between the complexity of the part you need, how fast you need to make it, and the overall cost you're willing to pay.
And all of this brings us to one final thought to leave you with. The defining feature of thermosets, the very thing that makes them so useful, their permanence, their inability to be remelted, is what makes them so incredibly strong and durable. But in our world, which is more and more focused on recycling and sustainability, you have to ask the question, is that incredible lifelong durability a bug, or is it a feature? It's definitely something to think about.